So, welcome to this class on hardware security. So, we were studying on power analysis. So, we shall be continuing our discussions with that. So, in particular, we shall be trying to continue our discussions on difference of mean based DPA attacks. I will start with how do you develop a setup which is very crucial for proper experimentations on DPA. We shall be discussing about power models, the various kind of useful power models that we generally encounter. So, I will be trying to discuss about two usual power models, like which are called as Hamming weights and Hamming distances. And then I will be discussing about another very important concept or component in power, which is essentially the intrinsic noise which is there, and we shall be discussing about statistical analysis of power traces, and we shall be trying to interpret difference of mean in a statistical setting or using statistical tools. So, let us start with this background. So, this is an overview about how a power attack setup typically looks like. So, if you observe, there are three important components here. So, you have got the design under test, which is essentially the where you are basically putting your encryption algorithm. So, essentially it could be an FPGA, it could be a smart card or a microcontroller, which is essentially the target of your attack. On the other hand, so this FPGA, so this is a, I mean, there are different platforms that you can of course target, but typically the platform that we will be considering are essentially called as Hasevo boards or Sakura boards. These are very standard boards which are available internationally, where we can do our experiments on power attacks and other kinds of side channels. So, this board is called essentially it has got two important parts, and out of them the most important part, there are two FPGAs in the board. So, one FPGA is the control FPGA, which contains the codes for communication with the CPU, and it acts as a controller which provides inputs and required control signals to the second FPGA, which houses the crypto algorithm. So, the crypto algorithm is kind of housed in the second FPGA, and the first FPGA or the control FPGA essentially does communication. So, it basically communicates with the CPU and it acts as a central controller. So, therefore, the objective of it, right, is I mean the controller or the control FPGA essentially has got the key role of performing communication with the CPU, and it is typically done through an USB cable. The other important component in this setup is the oscilloscope. So, the oscilloscope is typically used for acquiring power traces or electromagnetic traces or any other side channel traces that we essentially are interested in. And upon receiving, so there is essentially a trigger signal which the design generates, say upon like when every encryption is done. So, after every encryption there is a trigger which is generated. So, upon receiving this triggered signal, power traces are obtained and they are sent to the CPU. So, the triggering essentially indicates kind of the start of the encryption, and therefore, it helps us to align the power traces. So, that every power trace corresponds to the same set of operations. Okay. If there is a misalignment, then that would lead to lesser success rate. I mean, it can essentially lead to the fact that the attack will not work also. So, it is very important that we properly align the traces, and triggering helps us to do so. Now, the oscilloscope also needs to have a high sampling rate, because as we know that if the sampling rate is low, then it will miss information, and that essentially could be crucial for the attack. So, essentially it has got a high typically it has got a high sampling rate, and that is an important criteria for like getting a suitable oscilloscope. Then the heart of this entire operation is the CPU. Okay, the CPU or your computer essentially is where the whole setup along with the other the other components are essentially synchronized. So, therefore, the CPU as you can see over here is the PC, which provides the plain text to your target board, and it receives the corresponding cipher text, and at the same time it also receives the corresponding power trace. So, in a typical attack, like where you are not considering side channels, the attacker would probably have access to the plain text and definitely the cipher text. But here you also observe the side channel information, which is the power trace value. So, essentially it is the power consumption trace. Now, the power consumption is obtained by essentially by the oscilloscope, when the oscilloscope receives a triggered signal from this device, and then it starts kind of observing the corresponding signals, and essentially in this case the power signals, and these are transported back to the PC. So, the PC kind of maintains a repository of the plain text, the ciphertext, and also the corresponding power trace, okay, and it is nicely synchronized by the PC. So, the PC essentially plays a very pivotal role in doing this organization or synchronization. So, the power capture essentially will require you to have some very vital component of your setup, which is the probes. Okay. So, there can be different kind of probes. For example, you can see here some pictures of probes. So, you can see that there are some probes which has got straight heads and there are some probes which has got circular heads. Typically, these probes are used for injections and for analysis. That means, for example, when you are doing say power analysis, you will be using these probes which has got straight heads. Okay. And the operating frequency is also very vital for these probes. That means, the probes typically should have a high frequency allowance. That means, it should be able to pass the high frequency components. Typically, your power traces for these circuits can have high frequency components, and you do not want to miss those information, because if you miss it, right, you know that you are not getting the complete information about the power trace. So, therefore, the power trace typically has got in our case an operating frequency of around 30 megahertz to 3 gigahertz, and these are all based on near field probes. So, these are near field probes, means they are based on magnetic field. So, therefore, I mean in another setting, right, you can actually rip up the line between the voltage or the VCC and your setup, and you can implant or put in a resistor, and you can observe the current through the resistor. Alternatively, right, you can actually use these kind of probes through which you can, using the magnetic flux, right, you can observe the corresponding power consumptions. So, the other, as I said, the other important component or aspect is the sampling frequency of your oscilloscope. So, typically we set the oscilloscope sampling frequency as high as 2.5 gigasamples per second, which you can see that if your crypto FPGA frequency for the Sasebo or the Sakura board typically operates at 2 megahertz clock. So, if you see 2.5 gigasamples per second, 2 megahertz, that implies that the samples per cycle is around 1024, exactly 1250. Okay. So, this you can figure out from these two data, right, that the number of samples per cycle is 1250. So, typically, right, I would like that this value should be high. So, that like we get large, we do not miss any vital information about the power consumption in the trace. So, therefore, we require a high sampling an oscilloscope with a high sampling frequency. Okay. So, here is my design under test. So, of course, you can change the target, but let us consider this as our target. So, this is our rolled AES architecture, which we already discussed in our previous classes. So, the AES, right, essentially is also in this case only the AES 128 version, but you can easily extend it to other dimensions of the AES algorithm. And the AES in this case is implemented on Vertex 5 FPGA, and this is the device family of the FPGA, and it has got a triggered signal. As I said, that the triggered signal will basically indicate that the operation has been done after every encryption. So, this triggered signal's objective is to align the power traces, so that each trace profile corresponds to the same sequence of operations in an encryption run. Okay. The signal is tapped from the controller pin of the FPGA board and is fed to the second channel of the oscilloscope. Okay. And it kind of gives you a reference, so that you can basically align all the traces, because when you are doing a power attack, typically you can have like thousands of traces, thousands to millions of traces. Okay. So, you need to properly align these traces, and the trigger essentially is handy in that context. So, the plain text input is fed from the PC, and the ciphertext is fed back to the PC for correctness check. Of course, you need to ensure that your design is working properly as expected by in the AES algorithm. And the power trace from the board is acquired by the oscilloscope, and the power trace values are stored in the PC. As I said, that the power trace values are also recorded in the PC, because there we will do our statistical processing or DP attack. So, here is how the power trace of an AES algorithm looks like. As I said, that the crypto FPGA frequency is 2 megahertz, and you are basically collecting like 1250 samples per cycle. So, we did an FFT plot of this. The objective was to show like, so we basically when we are doing this FFT analysis, right, we ensure that the maximum frequency without aliasing is kept around 1.25 gigahertz. So, that means like if this trace, right, has got some frequency component which is more than 1.25 gigahertz, then that is lost. Okay. And When we do an inverse Fourier transformation, then we get back the original power trace, kind of showing that you do not have any component which is more than 1.25 gigahertz in this trace. Okay. So, this is a two sided frequency domain plot, and you can observe that essentially there is a central like the DC bias of this power trace, okay, and that is essentially shown by this 0 frequency component of the FFT curve or the FFT plot. So, let us before I go into the other aspects that we essentially I will be discussing about the high frequency component of the power signals and how they should be communicated to the oscilloscope. But before that, let us discuss about the power models, which is a very vital aspect of doing your differential power attacks. So, power model typically means it is basically a simplistic model through which you basically kind of estimate, or I would say rather guesstimate, the corresponding power consumption. Okay. So, you see that like you have got, in this case, just to explain that, I show a picture of a simple CMOS inverter, and you can see that there is essentially a PMOS and an NMOS basically stacked to each other. The objective is to charge and discharge a capacitor. So, the capacitor essentially stores the value of the output of this gate, and when it is charged, right, it is charged through the PMOS, and when it gets discharged through the NMOS. So, there is a distinct charging path and the discharging path. Okay. That implies that the power consumption should be different probably for the charging as well as the discharging. Okay. But before I even get into that, right, I mean, we should try to understand why do we need the power model in our attack. Okay. So, if you remember, when we were doing the difference of mean based attack, the objective was that you had the access to the ciphertext as an attacker, you were guessing a portion of the key, and based upon that you were trying to kind of like go back to an intermediate stage, to go into an intermediate state, and there you are basically applying a power model. Okay. And the objective of that power model would be to get some kind of estimate about the actual power consumption. Okay. So, power analysis depends largely on this simulation of power, okay, because you have got an actual power and you try to simulate the power, and then you try to correlate these two things. Okay. And the idea is that if your key guess was correct, or at least the guess for the portion of the key was correct, then the simulation would match with your expected or with your observed power consumption. Okay. That is the basic idea. So, power analysis depends largely on power simulation, which predicts the power variation of a device with respect to the change of internal values. The internal value is often computed from the ciphertext and the assumed portion of the key, and the power model which maps the internal power to a power level. So, this could be, for example, a Hamming weight or a Hamming distance model. Okay. There could be other models also. So, more than the actual value, what is more important is the relative predictions, like whether the power like increases or the power decreases, because I am not really bothered about the actual power often. Okay. I am more bothered about the relative ordering of the power consumptions. So, therefore, right, the unit is not so important. What is important is the relative ordering, okay, whether the power consumption is increasing because of a different data or whether the power consumption is decreasing because of another data. So, two popular models which is often very usually used, okay, very commonly used, are the Hamming weight and the Hamming distance models. Okay. So, if you see the figure, the Hamming weight essentially means that the power consumption depends at a time t of a CMOS gate, in this case an inverter, depends upon Vt, that means the voltage which this capacitor is holding. Okay. It does not really bother in this case, in this model, about what was the previous state of this or previous charge of this capacitor. Okay. So, therefore, I can kind of simulate the power by taking the Hamming weight of say V1. Okay. So, if you consider that if you stack this inverter in say like n number of times, and if you get a resistor, for example, then the like if you have got say the resistor is typically like a value which has got an n components. Okay. And each of these components can be say either a 1 or a 0. Okay. So, you have basically an n bit resistor. Okay. So, in this case, in this model, basically the idea is that the power consumption is dependent upon the corresponding Hamming weight, that means the number of ones in that n bit register. Okay. On the other hand, if you have a Hamming distance model, then that means that the power consumption depends upon the Hamming distance, okay, between this current state and the previous state. So, that would imply that if you have got a resistor which makes a transition from say V0 to V1, then the power is modeled by the Hamming distance of V0 and V1, which is nothing but the Hamming weight of V0 XORed with V1. Okay. That basically counts the number of switches. Okay. So, that means like in this case, what I am the power consumption at time t depends upon not only this current time voltage, but also on the previous value of the voltage. Okay. So, that means like it is more probably more realistic, because like when you are considering dynamic power consumption, then you would expect that a Hamming distance model probably would be more accurately estimating the power consumption. At the same time, right, also keep in mind that when you are doing a Hamming weight or if you are comparing the Hamming weight power model with a Hamming distance power model, in the Hamming distance power model you also need to know what was the previous state of that resistor, okay, which means that you need more information. Okay. And sometimes, right, that may not be like it may not be so easy to work with the Hamming distance model. Okay. But at the same time, we can try to, if you observe, right, you will see that the Hamming weight model also does not do so bad. Okay. One of the reasons, for example, like in certain category of implementations, as we know that in CMOS, right, in particularly when we talk about dynamic CMOS, we have got certain category of circuits which gets occasionally charged. Okay. Charged means like pre-charged. So, there is a pre-charge stage followed by an evaluate stage. So, in the pre-charge state, typically you like you can either charge a state to 0 or you can charge a state to 1. Okay. So, let us consider, suppose you charge it to 0 or 1, it does not matter. That implies that in the previous cycle, like you have a constant. Okay. And in that case, right, a Hamming weight model will work as good as a Hamming distance model. Okay. And you will see that these kind of circuits are not, so they are in quite abundance actually, like typically microcontroller circuits, right, or smart card circuits may have a pre-charge logic, and therefore, in such context a Hamming weight model may work pretty okay, pretty well. Even in other contexts where you are not doing a pre-charge, okay, suppose you are considering a cryptographic circuit, for example. In a cryptographic circuit, often the previous state is randomized, right, you basically have a random data, and in that in this say tth clock cycle you are doing a computation which is probably dependent upon the key, and you want to kind of sneak out that dependence by using a power attack. So, in that context you can also keep in mind that, as I said, that right, the power consumption is not really like, so in that case, right, if the power consumption was uniform, that means if the power consumption, right, was whether you are going from a 0 to 1 state or you are like going from maybe like a 1 to 0 state, if they were roughly equal, then you probably couldn't have worked with a Hamming weight model. Okay. But on the other hand, right, if you have a Hamming, if you have this skewness in the power consumption, that means when you are going from when you are charging to a 0 state or when you are charging to a 1 state, if they are dependent, like if there is a bias, right, then that would imply that it still correlates with the corresponding Hamming weight at the time t. Okay. And that means, right, even in that context, right, a Hamming weight model may work pretty well, even if you are not applying the Hamming distance model. Okay. But all said and done, definitely the Hamming distance model is probably more accurate, but a Hamming weight model also would probably work quite well. Okay. And it is therefore that we often use both in our attacks. So, here is an example modeling of an LFSR or a linear feedback shift register, which is implemented along with the nonlinear function. So, this is typically how a stream cipher is implemented. You have an LFSR block, you have a nonlinear feedback shift Boolean function to basically which works as a Boolean combiner, and then you have got the plain text. It basically generates a key stream, you XOR them and you get the cipher text. So, this is typically how a stream cipher would probably look like. Okay. So, what we do here is that we basically implement on a Xilinx FPGA device and try to observe the actual power taken as a voltage drop, the power traces for 80 consecutive clock cycles after you are deasserting the reset. So, you basically initially reset and then allow the stream cipher to generate key streams, and you also try to capture the corresponding power consumption. So, what we see here is that we basically develop two models using the Hamming weight model and the Hamming distance models. You can see that they are pretty much working, both of them are pretty much working accurately, and there is a good amount of correspondence with the actual power consumption. Okay. Although it will not exactly follow, for example, like in some cases, in some streak cases probably you will see an aberration, but if you see the overall tendency between this line and between these as models, you see that there is a good amount of correlation. Okay. And that shows like the efficacy of these models, like that these models are working pretty well in our normal for our normal targets or normal platforms. So then the question is, right, why do gates leak? Okay. So, here is an explanation or an analysis in that to answer that question. Okay. So, we consider an AND gate. So, an AND gate is in this case depicted by this function y equal to a and b, where a and b are just bits. Okay. So, consider 4 different energy levels due to the transition of the gates. So, the gate can make switches like 0 to 0 or 0 to 1 or 1 to 0 or 1 to 1. So, there are 4 different energy levels which it can take depending upon the switching that is happening. Okay. So, we basically kind of sort of tabulate the transitions of the inputs A, B and also observe the corresponding transition of Y in this table. Okay. So, if you see, right, what we do is we basically observe, we basically make what we do here is we just give the transition say 0 to 0 in A and consider all the 4 transitions in B, like it can make 0 to 0, it can make a transition from 0 to 1, it can make a transition from 1 to 0 and it can make a transition from 1 to 1. Okay. So, you can observe that if this makes a transition from 0 to 0, so basically the idea is very simple, like what I am trying to do here is that I am trying to basically take a gate. So, here you have got an AND gate, okay, and the AND gate has got 2 inputs, say A, B and the output is Y. Okay. So, what we are doing is we are basically considering all possible transitions in A. So, the A for example can make, so I also write a 0 to 0 transition as 0 to 0, or it can go from 0 to 1, or it can go from 1 to 0, or it can go from 1 to 1. Okay. So, there are 4 possible transitions for A. Okay. Likewise, there are 4 possible transitions for B. Okay. So, we basically combine all of these possibilities and therefore, right, we have got 16 possibilities of 16 combinations, right. So, imagine that A is making a transition from 0 to 0. So, if A is making a transition from 0 to 0, just to explain the first line. Okay. So, A is making a transition from 0 to 0 and B is making a transition from 0 to 0. So, therefore, it immediately implies that the initially, right, your A was at, the output was at 0 and it remains at 0. So, the Y remains at 0. Okay. Likewise, if you consider another case, like suppose let us consider this case. Okay. So, in this case we basically observe that suppose A makes a transition from 1 to 1, that means it was 1 and it remains at 1 state, and B makes a transition from 0 to 1. Okay. That means initially the AND, right, was at logic 0 and after this clock cycle, right, it becomes logic 1. So, therefore, it goes from 0 to 1. Okay. So, like this, right, we have basically kind of observed all the 16 possible transitions and then we basically write the corresponding energy for these transitions. Like suppose this gate is making a transition from 0 to 0. So, we basically kind of write or tabulate the energy consumption as E 0 to 0 and likewise here we write E 0 to 1. Okay. Similarly, right, in some cases we will have E 1 to 0 and we will also have E 1 to 1. So, these are the 4 energy energy levels that we are considering. So, now what we try to do is we basically try to calculate the average energy when the output is 0 and the average energy when the output is 1. So, if you remember in the difference of mean, we exactly try to do the same, right. We basically try to find out the average energy consumption in both the cases. So, we basically try to find out what is the average energy when the output gets converted into 0, that means gets computed into 0, and the average energy when the output gets calculated as 1. Okay. So, therefore, we find out EQ equal to 0 and EQ equal to 1. So, EQ equal to 0 are those cases where you have got the output which results in 0. So, you can observe that this is such a case. Okay. Likewise, this is a case where the output becomes 0, because likewise for all these cases you have got the output which results in 0. Likewise, here also in the black case also you have got a 0 which is the output results in 0, but this one, right, is a E0 to 1 transition, that means the gate becomes 1 after the transition. Okay. So, therefore, we will not put this in this bin and this is another case to be considered here. Likewise, these two are also important and we also have E1 to 0 which is essentially shown here. So, all these are cases which we are considering here, because the output gets transformed into 0. Okay. So, here you can observe that there are 9 E0 to 0 transitions, okay, like 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, there are 9 E0 to 0 transitions and there are 3 E1 to 0 transitions, like these blues are the E1 to 0 transitions. Okay. So, therefore, if you average, you get divided by 12. Likewise, right, for EQ equal to 1, there are 3 E0 to 1 transitions and there is 1 E1 to 1 transition. So, the average is essentially shown here, and you can observe that if the transitions like E0 to 0, 1 to 0, 1 to 1 and 0 to 1, okay, they are not identical, then EQ equal to 0 and EQ equal to 1, they are not same. Okay. And that implies that you do not have the same level or average power, and the power essentially correlates with whether the output is 0 or whether the output is 1. Okay. And therefore, right, this is an important or like I would say like a simple experiment, but it kind of shows that like that there is a correlation. So, therefore, this correlation is essentially one of the reasons why you have the gates leaking in context to power attacks. So likewise, right, I mean the other important thing is the quality of measurement and noise, and you can observe here that and you can easily point out that the high quality of power traces is very important and central to the accuracy of differential power attack. So, here in this case we do a very simple experiment. We basically run AES encryption with the same plain text and the key, but as you can see that the power traces are varying, okay, and it is resulting in different power traces. But if you want, right, that your power capture is accurate, then you would like to have this variation as small as possible, and this variation essentially takes place because of the noise which is essentially there in your implementation. Okay. So, these fluctuations are typically caused due to electrical noise, which are caused by noise due to power supply, clock generator, conduction and radiation emissions from the components connected to the device under attack. Okay. And therefore, this is an important aspect that we need to consider when we discuss about power attacks. Okay. So, I will be discussing more about about noise and also about how to kind of analyze noise, okay, using statistical tools, but that we will take up in the next class. Thank you.